Math 1325, section 4.4 today. So far we have done 1, 2, 3, 4, 5 of the 7 sections for this unit. We have 2 things left, section 4.4, derivatives of exponential functions, and then 4.5 is the same thing for logarithmic functions. I have also added the rest of the third unit is here now. So 5.1, 5.2, 5.3, 5.4. Those are the only things we do in chapter 5. And then in chapter 6, we just do 6.1, 6.4, and 6.5. And then the review. So all of this stuff's due November 11th. There'll be a third test that will pop in right here on November 10th. And then you'll have a 2-day window for that. Just like test 2 is going to pop in right here on October 20th. So October 21st, that's when all this stuff is due. The 2-day testing window is October 20th or 21st. Okay, so we did derivatives for the definition of them and doing them out the long way with limits. And then we've been doing a bunch of shortcuts for derivatives lately. So maybe we'll make a list here. We did these are derivative shortcuts. One is the power rule. And whether you have a function, polynomial function of x as one term or a bunch of terms, you just do them term by term. And if there's pluses and minuses between them, you keep the pluses and minuses. Constants in front can also be considered done separately, but if you have an ax to the b power, ax to the b, so x is the variable and a and b are just constants. The exponent is a number and the constant is a number. So then the derivative is a times b. You keep the x the same and then you decrease the exponent by 1. And then technically you're multiplying by the derivative of the base, which is x, but the derivative of x is just 1. So really the chain rule always comes into play, but a lot of times it just equals 1 and it seems like it doesn't matter. So we did the power rule first, which is covered under this, techniques for finding derivatives. Then we had both the product and quotient rule taught in one whole section. This is when you start off with 2 functions of x multiplied together. So if f of x is g of x times h of x, then the derivative is first function times the derivative of the second plus the second function times the derivative of the first, which is a good way to remember it. First times derivative of the second plus second times derivative of the first. Quotient rule. Two functions of x divided by each other. G of x divided by h of x. So now the derivative is second times derivative of the first minus the first times the derivative of the second and over the second squared. Last time we did the chain rule, which is kind of its own rule. It can happen at any time. Basically, all these other rules, including the kind we're going to learn next, this could happen anywhere. It's all about whatever you're working with. the original function f of x or these individual functions g or h of x, if any of them are other than just x, then while you're doing that derivative, you have to chain on whatever the derivative of that is. So in other words, this x right here might be an x squared instead. Well, the derivative of x squared is 2x, so then after you do the power rule, then you would attach a 2x onto the end of it, chain it on. So if you're doing f of x equals, this is when you have functions inside of functions, so if you have a g of h of x, then you do the derivative of the outside, g prime of h of x. You keep the h of x the same for a minute. Whatever the base is, you just keep it the same. And then you multiply by the derivative of the inside stuff. That gets chained onto the end there. So next up are exponentials, and then next video we'll do logs. Exponentials are probably the easiest rule of them all. The main rule is you have to know what an exponential function is from algebra. Exponentials backwards from a polynomial. In a polynomial, the base is x and the exponent is a number, and there can be a constant here or not, but the base is x and the exponent is a number. In exponential, it's reversed. So now you have the base is a number and the exponent is an x, and there can be times a b or whatever, but constants just come along for the ride in all the derivative rules anyway. So if you have an exponential a to the x, where one rule about exponentials is the base has to be positive and not equal to 1. Any positive number not equal to 1 is the base. A to the x, that's the derivative. Well, the good news is, that's the original function. The derivative of an exponential starts off as itself. It's the one derivative that equals itself, basically. The derivative of an exponential is itself. And then times, here's a little extra constant part, times ln of the base, natural log of the base. And then potentially times the derivative of the exponent. Well, that is there no matter what. But if the derivative of the exponent is 1, then it doesn't matter. But in essence, that's the chain rule. So if the chain rule applies, then you have to do it. And it will apply as long as the derivative of the exponent is anything other than a 1. Right now, I just have an x up here. So then the derivative of that's 1, so technically I'm multiplying by 1. So if it's not just x, say the original is a to the g of x. Say you have some kind of function of x there other than just x. Then I should draw an arrow here. Then the derivative of the function, you do just like the first one, you do itself, well actually I should write g of x here. You do itself first, whatever it looks like originally, that's what's there. Then you tack on a ln of the base, and then you tack on the derivative of the exponent. And even if it equals 1, you can think of it being attached on there. So if the exponent is just x, then it's like there's nothing at the end. It's really a 1 at the end. But if the exponent is not just x, which is most of the time, then you have kind of that third part. But for the most part, this is easy. The first part is you write it down exactly as it looks. Then you attach a ln of a, which is just some constant that goes along for the ride, and then potentially times the derivative of the exponent. One special case too is what if I have e to the x? E is a special number in math, 2.71828, Euler's constant. It's extensively used in upper level calculus classes. So it's actually the most common base of any base that we do with derivatives. Much more common than just like a 2 or a 3 right here. So it's really the same rule, though it actually shortens slightly because, whoops, if I'm doing the derivative of g, the rule is exponentials, you first get itself as its derivative. Every exponential has itself as its derivative times the natural log of the base, and then potentially times the derivative of the exponent, but here it would just be a 1. That's always a chain rule at the end. So I could have e to the x squared, for example, and then I would have to attach on a 2x at the end. The only difference, though, is ln of a is going to be in any answer where the base is any positive number other than 1 and other than e. Because ln of e is a special case that equals 1. It's one of the properties of logs is that ln of e equals 1. So the derivative of a to the x, if a is just some generic base, is a to the x times ln of a. That's kind of the main rule to know here. But if your original function is e to the x, then the answer is literally just e to the x. That's really the only one that's itself, because these other two parts are ones and don't matter. And then, of course, if the derivative of the exponent is something different than 1, then we'll attach that on too. Okay, so section 4.4, 10 problems. Okay, so determine whether the statement is true or false and explain why. A function can be both an exponential function and a polynomial function. That is definitely not true. The difference between them is they're backwards of each other. Exponentials are like this, where you have a base of 3 and an x in the exponent. Polynomials are exactly the reverse, where the x is the base and the 3 or whatever number is the exponent. So B and C are definitely wrong. It's not true. Statement is false, A or D. A function cannot be both. In a polynomial function, the variable is in the exponent. No, that's exponential. In an exponential function, the variable is in the exponent. In a polynomial function, the variable is never in the exponent. While in an exponential function, the variable is the exponent. Yeah, it's exactly D right here. So that's why they have different rules. The polynomials are dealt with the power rule, but exponentials are not done. You don't use the power rule anymore. So that's, I guess, the point of this question is, if somebody gets 3 to the x as a problem, you don't do the power rule. You don't do x times 1 and write the base and put x to the 3 to the x minus 1. So don't mix up the rules, I guess, is the point of that. And then this is a true-false, but this is going back to the definition of exponentials from algebra. An exponential function can have a negative base. No, by rule, they're not allowed to. So it's just a rule in exponentials that you cannot have a negative base. The definition of an exponential states that the base cannot be negative. And the reason why is because then you could get mixed up with reflections. And we have reflections where the negative isn't attached to the base, but we don't do reflections over the y-axis because that's handled with a base that's less than 1. So those two are just kind of FYI, so you know that. Here comes the first actual real problem. So I have f of x equals 3e to the 3x. Notice that e is a very common base. We're going to see most of the problems have that, where other bases will come up occasionally. So problem number 3, the original function is f of x equals 3e to the 3x. Don't try to use the power rule here. Don't do 3x times 3. That only works on polynomials, not on exponentials. So this has its own rule. The derivative of an exponential is itself first. You always just rewrite it as itself. Technically, there's a ln of the base. But if ever the base is e, that's equal to 1. And then times the derivative of the exponent. That's the chain rule. So the derivative of 3x is 3 because 3x is linear, so then the derivative is just the slope in front 3. So ln of e is 1, so then it doesn't matter. The 3 matters, so I could do this 3 times that 3 since they're both constants and get 9. And then there's e to the 3x. So whenever you see e to the 3x, the derivative is gonna have that in it. The original exponential is always in the derivative answer somewhere. So 9e to the 3x, that's simple. So these problems don't take very long. This video might not be that long, but 9e to the 3x. Okay, number 4, y equals negative 4 e to the negative 4x plus 1. Negative 4 e to the negative 4x plus 1. So I'm going to write either y prime or maybe dy over dx. Those are synonymous. Always rewrite it exactly like it looks first, no matter what exponential you have. That's always there no matter what. Then there's technically an ln of e, which will cancel out since we have other stuff. And then the derivative of the exponent matters. This is linear still. Negative 4x plus 1 is like mx plus b. The slope of that's negative 4. So the derivative of negative 4x plus 1 is its slope in front, negative 4. And then we can actually do the negative 4 times the negative 4. That makes positive 16 e to the negative 4x plus 1. 16 e to the negative 4x plus 1. Okay, y equals negative 2 e to the negative 4x squared. Negative 2 e to the negative 4x squared. So either y prime or dy over dx. So you're going to write it exactly like it looks first every time. Don't try doing the power rule. Negative 2 e to the negative 4x squared. Technically times an ln of e. And then now I need the derivative of this exponent. This one's not linear. So this exponent is a polynomial function. So it's like you have a g of x. You have a separate function of x inside of the main function. So just like if you had g of x equaled negative 4x squared back in the beginning of the chapter, the derivative of that is the power rule because that's a polynomial function. So that would be 2 times negative 4, negative 8. X to the 2 minus 1 is 1. So the chain rule part could be the power rule if that's what you happen to be doing. The exponential part itself will never be the power rule, but the exponent of it could be. So now do negative 8x times negative 2. That will be positive 16x. We usually put that in front. Exponentials usually go in the back. If the ln was something other than e, then we would just attach that either to the front or the back. But since it's ln of e, that equals 1 and disappears. So 16x e to the negative 4x squared, and the e to the negative 4x squared was in the original problem. But you probably wouldn't have guessed 16x from a negative 2 right there. 16x e to the negative 4x, and now I need another exponent button, squared. Okay, so now let's see if you recognize this. Now they're going to start throwing multiple rules at you at once. Y equals x squared times e to the x. Always look for variables. That can give a hint of what you're actually doing. X to the 12th, that's a function of x all by itself. Times e to the x, there's another function of x. This is my first function of x. This is my second function of x. I don't just have a constant like these previous problems. This is not a function of x. This is a constant. This is not a function of x. That's not a function of x. You got to have an x attached to those. There could be. This could have been 3x times e to the 3x. This could have been negative 4x. This one could have been negative 2x. And then it'll be done like this problem if they were. Now I do have an x here and I have an x there. They're multiplied together. That's the good old product rule. Product rule. First times derivative of the second plus second times derivative of the first. And in the process of doing that, I might hit this new rule, which we are going to. So product rule, I'm doing first exactly as it is, times the derivative of the second. Well, the derivative of e to the x is itself. That's the easiest one of them all. The derivative of e to the x is literally e to the x. The ln of e won't matter, and the derivative of the exponent won't matter because the derivative of x is 1. So the easiest exponential of them all, they're all easy, but the easiest one is e to the x. It's the only one that stays exactly the same as the original. So this was first, and maybe it doesn't look like it, but this was derivative of the second, plus the second, which is again just e to the x, times the derivative of the first. The derivative of x to the 12th is 12x to the 11th. So we could make this look a little nicer by pulling out a greatest common factor. Both terms around the plus have an e to the x. That's common to both parts. And then they both have x, a power of x. So when they both have x to an exponent, then you take the smaller one for the GCF. So I need an x to the 11th times an e to the x for the GCF. Then there would be one more x here. There was 12 x's here. I took 11 of them out, so there's one left. I already took the e to the x, then the plus. I took the e to the x and I took the x to the 11, but I didn't take the 12 yet, so plus 12. So it's not always necessary to do this step, but later we might need to do that. We're going to get to a future chapter where we try to figure out where these things equal 0, and that's often very helpful to do that. It's easier to set something equal to 0 when it's a product than when it's a sum. So then we would check each of these parts for when they equal 0. That's going to come up next chapter, actually. So x to the 11th, e to the x, that's all multiplied together, times x plus 12. I've got it kind of in factors this way. E to the x, notice the x up in the exponent. So then right arrow to get out of the exponent, parenthesis. And what did I have? I had x plus 12. That was a good example of the product rule, while inside the product rule we had an exponential to do, although exponentials are easy. So now, same thing here. Now we have a function of x divided by another function of x. That's the quotient rule. So y equals 4e to the 4x in the numerator. That's a function of x. And then the denominator is linear, 9x plus 2. dy over dx, derivative of y with respect to x. But now we're going to do quotient rule. So second second times derivative of the first. That's what we're doing in this section. So you just kind of off to the side say, okay, what if I had this as my whole problem? What's the derivative of this? Well, it's itself first times ln of e, which equals 1, and then times 4, the derivative of 4x, which is just 4. So 4 times 4, that's 16 e to the 4x. That part alone was like problem 3 or 4, really. Just like those. But I'm still halfway through the quotient rule, so minus the first times the derivative of the second, although that's pretty easy. The derivative of 9x plus 2 is just the 9. And then over the second squared. Okay, so we could certainly distribute this. And 9 times 16 is 144. Whoops. Yeah, 144. So we could get a 144 x, make sure I don't miss my x like I did the other day, x and e to the 4x. That's typically the order when you mix constants and regular x's and exponentials. Then I can put plus 2 times 16 is 32, and that's just a regular 2, times 16 is 32 e to the 4x, minus, and I could do 9 times 4 and get 36 e to the 4x. Over the second squared, which again, usually you just keep rewriting that all the way to the answer. See, by doing that distributive property, it helps because now we have like terms here and here. This one's not a like term, though, because it has an extra x attached. These are just 32e and 36e. And to the 4x also is important. So they're only like terms if you have different numbers, possibly, or the same number, and all the rest has to be identical. E to the 4x is identical to e to the 4x. If it was e to the 4x and e to the 3x, they would not be like terms. If one has an extra x and the other doesn't, those are not like terms. Okay, so then I could put 144x e to the 4x. And then I could subtract this 32 minus 36 and get negative 4 e to the 4x. Over 9x plus 2 squared. So this could be the answer. And it would be as long as I can't factor and cancel the top. You certainly could do a GCF in the top if you want to. And it's always good to just check that just in case. So both 144 and 4 divide by 4. And they both have an e to the 4x. And the second half, I took the entire thing out, so the second half is just going to be minus 1. In the front half, whatever 144 divided by 4 is, 36. 36x, because I took the e to the 4x away. So I was able to factor the top using a greatest common factor. And then, if somehow, it's very rare, but sometimes this parenthesis part matches this. It's really rare to get it to happen, but I've seen it happen a few times. If that happens, then you have to cancel this with one of these two, and the answer would be this part over just one of these. So if you can factor and cancel, you have to do it. If you can factor and it doesn't cancel, then you don't have to factor. But you don't know until you check. But now that I see that it doesn't cancel, then I could put this answer in. But if it could cancel and you leave it like this, then that's the rare time that it would be counted wrong, actually. So it's always good to, that's why even though on that last problem you might not have had to do this either, It's just kind of a good habit to at least check that real quick, just to make sure. Plus later it helps to do it too. So these are algebra skills that a lot of students have trouble with. Even people that go to real calculus, like this is business calculus, but people go to calculus 1, calculus 2, calculus 3. They do a lot harder stuff than we're doing, but even there, they have trouble with real basic algebra stuff like factoring. So I'm going to put it in the way I circled it, since it didn't factor and cancel, it only factored. So I'll put this version in 144 x to the x e to the 4x minus 4 e to the 4x, and then 9x plus 2 quantity squared, minus 4 e to the 4x, yeah, minus 4 e to the 4x. So because you could factor it, but it doesn't help me to cancel the bottom, then this answer should be acceptable. And in homework, you can always just try it and put it in. As soon as you reach that point, put the answer in and see if it takes it. But if you can factor and cancel, then they count it wrong to leave it this way, even though that doesn't happen very often. So just a little warning there. Okay, 8. For the first time, we see one where the base is not just e. Y equals 7 instead of an e. The base can be any positive number besides 1. 7 to the 6x plus 1. But it's really the same rule. The derivative of y with respect to x, any exponential, it starts off always as itself. Now we multiply by ln of the base. Ln of 7 is just some messy decimal number. 7 ln, see it's 1.94. It's kind of like square roots out there are always messy decimals. So this is just a constant, but it makes a difference. It's almost equal to 2. But if you do ln of e is 2.718281828. If you type e and then hit ln, it says 1 exactly. That's because they're opposites of each other and cancel out and equal 1. But ln of anything besides e is not equal to 1, and then it matters. And then the chain rule, the derivative of the exponent would be 6, so I need to check that on too. But both of these are just constants. So in the end, we always put the exponential part in the back, just so it's clear what's going where. I would put this regular 6 out front, times the ln of 7, which is a messy decimal, so we'd rather leave it like that, times 7 to the 6x plus 1. That's the most common way to write it. This isn't wrong to write it this way, because in math, 4 times 3 is the same thing as 3 times 4. That's called the commutative property of multiplication. In multiplication, order doesn't matter. So if you have 3 things multiplied together, you can mix it up in whatever order you want. But just to make it easier on the reader, we put a regular constant first so they notice that. Then ln of a number next, and then the exponential last, so we know where the exponent starts and stops. When you put something like this in this order, somebody might think that's ln of 42, even though it isn't. It's not equal to ln of 42. This 7 times 6 doesn't go together. It could, but only if it was in parentheses. There could be a case where I need to do ln of 2 things multiplied together, but these were each found independently. This was one answer and this was another, and they just happen to be multiplied together because that's the chain rule. So it just avoids confusion. This 6 is not part of this log now, but here you might think that it is why we don't like to write it that way. But I'm sure if you typed it in the homework this way and clearly put a times 6 that was separate, that would be an acceptable way to type it. But for us humans that like to communicate with each other to make it easier on the reader that you're communicating with, it's more common to do this. There's a lot of unwritten rules of math too that if you aren't familiar with them, you might do something that's considered like violating an unwritten rule, kind of like in baseball where they have People get upset about certain things that aren't actually in the rules. 6 ln of 7 times 7 to the 6x plus 1. And notice the original is in the answer as always. The original is always in the answer somewhere whenever you're doing exponentials. Okay, so now we have e to the, in the exponent, not only is there an x up there as always for exponentials, but there's two functions of x up there. So number 9, e to the x square root of 5x minus 3. So derivative of any exponential is itself first. It's always in the answer too. Since I have a base of e, there's technically an ln of e, but that will equal 1. And then I need the derivative of this. So what if I was working earlier in this chapter, and what if the original problem looked like this, and they said find the derivative of it? What if this was like an h of x somewhere else, just its own problem? Well, this is a function of x, this is a function of x, and they're multiplied together, so that's product rule. The derivative of this just on its own is first times the derivative of the second, and you might want to rewrite that as 5x minus 3 to the 1/2 before you do the derivative of it. So this derivative on its own, this is a chain rule really, because you're going to do the outside first, 1/2 5x minus 3 to the negative 1/2, and then chain on the derivative of the inside, which is a 5. All of this right there, that's just the derivative of the second part of this problem. Plus the second as it is, whether you want to write it as a radical or a 1/2 power. Second times the derivative of the first, the derivative of x is 1. So at least that part's easy. Looks like a minus, but it's supposed to be a times right there. Okay. So we could write this as x over 2, and then move that negative 1/2 to the bottom and put it back as a radical if you want. Plus, this would just be the square root of 5x minus 3 in the top of the fraction, basically. So this is one way to write the derivative. And we can just attach this onto the end. Now, the one issue is it would be all multiplied like so, not just the front part multiplied. So x over 2 square root of 5x minus 3 plus the square root of 5x minus 3. And of course, you don't have to write the square roots. You could leave them as 1/2 powers. You could even leave a negative 1/2 power in an answer. So this is another example of one where there's multiple ways to write the final answer. And then I could move all this to the front if I want to put the exponential in the back too. So let's try that and put x over 2 square root of the 5x minus 3 plus the square root of 5x minus 3. Whoops. There. And then times the original e, whoops, hit the cap locks, e to the x square root of 5x minus 3. Two over x over 2, just double checking I typed it right, x over 2 square root of 5x minus 3 plus, yeah. Product. Oh, I know what I did wrong, chain rule. Then see, chain rule can happen more than once. So where was I on this part? Okay. So we did the original times ln of e times this. Okay, so the derivative of this was the product rule. So where was I? First times derivative of the second. See, oh no, I have it there. Here it is. I thought I forgot to do it, but it's there. I just didn't put it in the answer. So I missed my times 5. That would just stay in the top of the fraction. But the derivative of this has the chain rule applying to it, the 5. I thought I forgot to do it, but it was there. I just forgot to write it. So put that 5 up there in the top. There should be an extra 5 up here. There, 5x. Yep, okay. See, that's a case where on a test, since we don't do our tests in class on paper, anybody could have a slight brain cramp like that and leave something off that they actually had correct. I actually had it correct, but I didn't put it in my final answer. So then, unfortunately, my math lab, they just count the whole thing wrong, even though it was really close to the right answer and I had it right on my paper, but that's how it goes. So if I was taking this test, I would have missed that problem just from a brain cramp mistake. Okay, number 10, the sales of a new high-tech item in thousands are given by the following function. T is time in years. Find the rate of change, so that's derivative of sales. And notice it's an exponential, okay? So always, whenever you get word problems, they're always whatever the section's about. So S of t equals 96 minus 90e to the negative 0.3t. We're definitely going to be doing the derivative off the bat. And let me reread the parts again. Well, it says find the rate of change. I thought that might be a part A, but that's the directions for all the parts. Find the rate of change after 1 year, after 5 years, and then so on. So part A, the rate of change after 1 year. Round to 3 decimal places. So we're going to find the derivative and plug 1 in after that. But I'm going to leave it in general terms first so that I can do it for other numbers after that more quickly. So the derivative, this is where you could get mixed up what rule's going on here. There's definitely an exponential rule going on. But this is minus right here. This is not times, and this doesn't even have a t attached to it. So I don't have multiple functions of t going on, and it's definitely not a quotient or a product rule when I have subtraction. So this is just going term by term. The derivative of the first term, that's a constant. The derivative of any constant is 0 if you're adding or subtracting that constant. If you're multiplying or dividing it, then it just comes along for the ride. Now I want to do the derivative of this, which is itself at first. Remember, any exponential you do itself first. Technically times ln of e, which won't matter here. And then times the derivative of the exponent, which is just a single function of x. It's not even exponential, it's just linear. So the derivative of that is negative 0.3. This 0 doesn't matter. Then just like those early problems, problem 3 and 4, remember how, well, that's not that one too, kind of, but remember how I was just getting a constant here at the end from the derivative of the exponent, and then that would get multiplied to the front constant. So that's what's going to happen here, is this back constant can be multiplied to that front constant. Negative 90 times negative 0.3 is positive 27. So the derivative of s with respect to t is positive 27 e to the negative 0.3t times 1, which doesn't matter. So the actual part A then is going to be s prime of 1. And then there'll be a part B where I do s prime of some other number. That's why it's good to have the derivative in general first. Doing the derivative in general first, then if I have to plug multiple numbers in, it's just real quick to do another one. So s prime of 1, and then we'll do s prime of 5 after that. So 27e to the negative 0.3 times 1 is 27e to the negative 0.3, and they did say round to some odd amount of decimals. So that's when using decimals in a calculator is fine. So e raised, here it is, raised to the 0.3 negative is how I have to do it in this calculator, times 27. If you do it in a graphing calculator, you would actually type it just like you'd read it out loud. 27e to the negative 0.3. I could show you that in a second. So 20, how many decimals do they want? 3 decimals. And the fourth decimal is a 0, so we don't need to add one. 20.002. So let's double check it with a graphing calculator. Here I type it just like you'd read it out loud. 27, the E button in a graphing calculator, it's hard to see it, but on my division button, right above the division button in yellow, there's a little E symbol, and then there's pi if you ever need pi. There's the E symbol in yellow, so you have to hit the yellow key first. Second, and the division sign gets you E. So 27e, and then this right above the division button, there's an arrow up button. That's for exponents, raised to the negative 0.3. This one I just type it in order, and I got the same answer, 20.002. In the other calculator, I actually had to type E first, then raise to the 0.3, then hit the negative button, then multiply by 27. Almost doing it completely backwards. 20.002. Okay, now wait, because this is in thousands, and this is thousand. Okay, so you always got to make sure they didn't change the units. Sometimes this is like in millions, and this is in thousands or something like that. Then you got to worry about where the decimal might go. So now do it for 5. 27e to the negative 0.3 times 5. So it's easier in here. I can do 27 second, and the negative key gets me E, raised to the negative, that would be 1.5. So I should have multiplied this out first. 27e to the negative 1.5. If you do negative 0.3 times 5, that's negative 1.5. And that was 6.0245 or 025. And then let me do it on the other calculator to double check. Here I would hit the E button first, which gets me 2.718, and then raise that to the 1.5, then hit the plus minus button to make it negative 1.5 equals times 27. 6.0245 or 6.025. So whether you have a graphing or a scientific calculator, you can get this answer right. 6.025. 1,000 items per year. What is happening to the rate of change of sales as time goes on? As time goes on, notice this is getting smaller from 20 down to 6. And part of the reason why for that is when you have e to a positive exponent, the graph increases in algebra. That's a graph that rises to the right. But if you make it negative, then it falls down like a exponential decay. So this is like exponential decay, and it's just going to get lower and lower and lower. So it's always decreasing. And then will it ever reach 0? The answer to that is definitely no if you know your exponential graphs. Whether you have an exponential growth or an exponential decay. Remember, growth goes like this. And decay comes in this way. We have this one right here where it's getting smaller and smaller and smaller. So exponential graphs, they always either increase always or decrease always, one or the other, depending if you have growth or decay. And that's based on whether you have a base that's bigger than 1 or less than 1, and then possibly if there's a negative up in the exponent, that can flip it. So that's what's happening is we have a base that's bigger than 1e, which normally does this, but then when you put a negative in the exponent, e to the negative flips it over the other side, so it goes this way instead. But both of these graphs have a horizontal asymptote of y equals 0. So you never equal 0. You can never get to 0. If you have a radioactive material that's losing half of its substance every so often, they call that radioactive half-life. So maybe 1,000,000 years ago it weighed 10 pounds and now it weighs 5. It took like 1,000,000 years for half of it to disappear. It will, even though it's constantly disappearing, it never goes to 0. And that's the basis for carbon dating, when they get like an old fossil and they can tell you this fossil is like 1,000,000,000 years old. Okay, so it never reaches 0 because of that horizontal asymptote. Something we learned in the beginning of the textbook when we were reviewing algebra items. Okay, so hopefully this section wasn't so bad. We did all 10 of them. 100% there. And it was all about exponentials. So I can save this. And now in my assignments tab, we have completed 3.3 all the way to 4.4. The next video will be section 4.5. That'll be the beginning of next week. The first half of next week is reserved for 4.5. Log functions, they're similar to exponentials because they're inverses of them. It turns out the rule is very similar, just you divide by ln of the base instead of multiplying by it. And then the review will be the second half of the week, and then you'll take your test next week, Thursday or Friday, October 20th or 21st. The test will appear right here between the review and 5.1 once we get to October 20th. And then we'll be set for a third unit that's chapter 5 and 6, basically just whatever sections in chapter 5 and 6 we cover, all chapter 5 and 6. And then we end the year with some chapter 7 stuff. So this video was a little less than an hour, and that's fine. We had a nice easier section for once that didn't take as long. And then logs will have 10 problems here too. Maybe that will go about the same amount of time. So see you next time for logarithmic derivatives.